Okay, well, good afternoon, everybody. My apologies for not being able to be here in person for this lesson, but the good news is this one's fairly straightforward, I hope. As you can see, we're on exercise 30, and we're going to deal with a topic called permutations today. Now, I've already written down the formula there for you, so I'll give you a second to copy that down. Hopefully, the factorial notation is becoming a lot more comfortable. Just a quick review, though. When you have something like 4 factorial, of course, that's really representing 4 multiplied by 3, then by 2, and then by 1. And of course, we've been working with some problem solving, some counting type problems using factorial notation. Well, today I'm going to extend that just a tiny bit further, and we'll discuss how permutations fits into that. So, I'm going to begin by refreshing your memory on a problem we solved before the midterm exam, and that had to do with a race involving 12 runners, and they wanted to know in how many ways the first 3 could finish. So what we did was we drew 3 little bars like this, and we said, well, out of 12 runners, any one of the 12 could finish first. But once that person had finished, there was only 11 runners left. So that would be 12 times 11, and then of course after the first 2 had finished, there was only 10 runners remaining to finish third. And so our answer would be found by doing that. Now, what I'm going to do is I'm going to show you how this permutation notation actually fits in. What we would do to use permutations is we'd say, well, there's 12 runners, and 12 permute 3. That really means I'm going to have 12 objects. In how many ways can I arrange 3 of them? And that works out when you use the formula to 12 factorial divided by 12 minus 3 factorial. Okay? And of course, when we go to simplify that, just extend the page here a little bit, we have 12 factorial over 9 factorial. And of course, we learned how to simplify our factorials down a little bit. So I should put that inside the bracket, like so. And of course, that's divided by 9 factorial. So what happens now, of course, is we do some reducing, and the 9 factorials reduce out, and we're left with the answer we had learned how to find before. Now, you might be asking, well, why would we need a formula for this? The snag is that with the permutation notation, we can begin to answer more complicated problems, and it allows us to sort of write this as opposed to this. And of course, this allows us to, simplify our expressions somewhat sometimes if the problem gets to be horribly complicated. So this is the notation that we want to move to for solving problems very similar to our runner type problem, like that. Okay? Now, in general, what I find is this. The problems that you're going to run into always seem to be a little bit different in one way or another. So, if you can kind of remember an example problem, and relate some of the other problems to it, it'll usually give you a place to start anyway. Okay, so what I want to do is I'm going to flip to the cumulative exercises here, and let's find a problem that we might take a look at. Now, something like this question here, write an algebraic expression for these, okay, especially part B, that's just some tricky sort of notation and some algebraic simplification. I'm going to leave that for you to play with, because it's mostly straightforward, and I mean, it takes some practice. It's not that it's simple necessarily, but that's something that we can sort of discuss, you know, at the board and practice a bit. Here's a problem that tends to come up more often than not, and so what I'll do is let me just copy this over and flip to a new page. We'll take a look at it. Now, so here we have 5 students, and they come into a French classroom with 10 desks. Now, how many different seating arrangements are possible? So again, what we want to do is we have 10 desks to choose from, and what we're going to do is we're going to arrange the 5 students. Okay, so 10 permutation 5. So this is going to look like 10 factorial over 10 minus 5 factorial, like that. And of course that's going to simplify out. Do 10 divided by 9, by 8, by 7, by 6, and then by 5 factorial. And on the bottom, we have the 5 factorial. And now we can do some reducing. And we'll be left with our answer. 10 times 9, multiplied by 8, 7, 6, and, oops, got carried away there. There we go. Now, again, we could have solved this problem using this approach. Okay, so we have 5 students, and the first student has 10 desks to choose from. Once that student has chosen their desk, the second student has 9 desks to choose from, and so on. And so you'll notice that we come up with exactly the same answer. Now again, I'm going to state this again. This method works fine. There's nothing wrong with it. However, sometimes the problems will become too complicated to draw that many bars out and start putting things in. So that's why we would move towards this. Okay? Now you're going to find that most of the questions in today's exercise, okay, can be solved using the dashes. Okay, same thing with number 6. In fact, I'll tell you what, now that I've looked at it, let's run through this one as a second example, and before I set you loose on this. Okay, so 4 entrances, 9 exits. How many ways can 2 people enter together but leave by different exits? Now, initially this sounds like a fairly difficult problem. However, if you remember that they have to enter together but leave by different exits, it's not so bad. Now, again, using the little dashes, there's 4 entrances for them to choose from. Now, they have to leave by 2 different exits. So the first person will have 9 exits to choose from. The second person will then have 8 exits to choose from. And so that's how that problem is solved. Using the permutation notation, what we're going to have is 4 permutation 4, and this is the number of ways they can choose an entrance, number of ways to enter. Okay? And that is going to be multiplied by 9 exits, and we're going to arrange 2 of them. And so that is the number of ways to exit. Now, you can kind of see where this, to me, is a problem that demonstrates why this notation, even though it's new and it seems a little bit uncomfortable, is a bit more straightforward than being able to solve it this way. Again, it's a simplified problem so that you can get used to using this notation over here, but it still can be sort of counted, which is this method. I call this more of a counting approach. Okay, and of course this is using permutations. Okay, now a quick side note actually, and then I'll let you get to your assignment. For permutation 4, when I was writing that down, it occurred to me that if you follow the formula on this, you end up with 4 minus 4 factorial. And that's actually one of the weird things about factorial notation. 0 factorial has this odd definition of equaling 1. It seems counterintuitive because 0 times anything is 0, and yet 0 factorial would be 1. That's just sort of to make this formula work. That's why that definition is there. If you have 4 objects and you're going to find out how many ways to arrange them, you have to end up with 4 times 3 times 2 times 1. That's how this has to simplify. It has to simplify to this. Now, to make the formula work then, we have to take into consideration the possibility of when we have a 0 factorial in the denominator. So we define zero factorial as equaling 1. So please make sure that you make a note of this so that you don't have any issues when you're doing the work. I'd like you to take a look at exercise 30 today and complete as many of these problems as you can. The first couple I hope are fairly straightforward. This, of course, here is number 3 here is kind of an algebra sort of problem. The problems, in my mind, do get progressively more difficult, but they go down to all the way down to number 10. Now, of course, as always, please try and continue with the rest of the exercise for review's sake. There's a nice identity here on the back that you can give a try, and of course, you want to keep your logarithms fresh, as well as your natural exponents. And here's a good trig problem. Now you'll notice that actually with these exercises now, the review problems, they're covering quite a few topics. So it's important that you get to as many of these as possible each day so that come exam time, we're definitely ready. I hope that's enough to get you started. And again, I should hope to see you probably again on Thursday. Good luck.